Hello, everybody. Welcome back. This is going to be lesson 6. We're going to be talking about the intermediate value theorem today. But for now, let's review the homework answers. So if you did the homework yesterday, you'll know about what I'm talking about. So these are the answers to the homework for anyone who wanted to know them. It's 5. It's 5. For anyone thinking, yeah. It all looks fairly traditional, but this was pretty difficult because there were 2 vertical asymptotes instead of 1. So yeah, this was tough. So I can understand if you might have struggled with this, but for now, this is the homework. All right, so that's pretty much it for the homework. Now we're going to move on to lesson 6. Lesson 6, intermediate. You'll have to forgive my handwriting here. Theorem. Intermediate value theorem, or as we call it, IVT. Incredibly important. It is one of 3 value theorems that you will learn. All right, let's get into it. So what is the intermediate value theorem? Theorem. This is going to be a pretty basic theorem. It basically states that if a function f, let's just call this f of x, is continuous on an interval a through b, and a specific number, we'll call it n, and f of a, and let's just say a number n is between f of a and f of b, meaning f of a less than n less than f of b, then there must be a value c where f of c is equal to n. This is a long thing. This is very hard to comprehend. So I'll try making it a little bit, I'll try to make a little bit more sense. So yeah, I'll draw it graphically so that you can see it. So let's take this function, f of x. We'll call this function f of x, right? And then we'll call this point f of a. I mean, we'll call this point a f of a. We'll call this point b f of b, right? Basically, what IVT is stating is that there must be a point c between a and b where f of c is going to be equal to that number n. Because remember, f of a is less than equal to n is less than or equal to f of b, meaning it has to be somewhere in between this and this. Meaning, no matter which point you choose, there must be an x value for that particular y value if the function is continuous. on the open interval. Well, yeah, it's on the open interval. But if you were looking for like a specific value that is the endpoint, then it's a bit different. Like, for example, if the n that you're looking for is f of b, and it's an open interval instead of a closed interval, then obviously that creates some issues. But for most cases, it's on the open interval. Let me just confirm that really quickly. Let me just check that really quickly and make sure I am correct with this information. I believe... Oh, it's not the open interval. It is the closed interval. All right. It must be the closed interval. My apologies. My memory slipped past me there. So it's not going to be not the open interval. Why is it not the open interval? Because the particular function n, the particular value n could be f of b or f of a. And if it's on the open interval instead of a closed interval, those 2 points may not exist, interfering with that with the theorem. All right, so let's see an example that we're going to work with mathematically. Most of the time we've been working with graphs. Now we're going to actually start working with some math here. X squared minus x plus 1. Now let's go with something a little bit spicier. We'll go with 4x cubed plus 3x squared plus 2x plus 1. And this will be this function f of x, right? And you basically, what I'm going to ask you is for the interval 1 to 5, which we know this is a parabola, meaning it must be an open, it must be continuous on this closed interval. For the interval 1, 5, is there a value that is there a value where a number in the for a value between, like a value n, a value n between the interval where f of n, f of n, oh my god, my apologies. Is there a value n between the interval where f of n is going to be equal to a particular number? So we'll choose 0 for our intensive purposes, where f of n is equal to 0, right? So how are you going to do this? Well, first we need to prove this function is continuous. And, we already know that it is continuous. So we need to justify it. Most of the time it'll ask us to justify our answer. Right? This is the important part. So what you want to start with is you want to check what value is f of 1 and what value is f of 5 guaranteed for on this given interval, right? So I'll let you think about this, and then I'll give you the answer in a minute. Yeah, normally I don't do this, but since we are pretty into it, I'll let you think about this one for starters. Yeah, I'll let you think about this one. I'll give you a minute to think about it. Please feel free to pause your screen, take a minute, check your answer, and just make sure you understand what's going on here. So basically, what we have to do is we have to take the value of f of 5, and we have to take the value of f of 1. And again, since it's a polynomial, we know it's continuous, right? And for all intents and purposes, this means that our values of a and b are 1 and 5. So this is f of a, this is f of b, right? So let's start by finding that value of f of 1. F of 1 is going to be equal to 4, 1 cubed, plus 3 squared, plus 2 times 1, plus 1, which is going to be equal to 4 plus 3 plus 2 plus 1, which is 10. And then we're going to move on to f of 5, which is going to be 4, 5 cubed, plus 3, 5 squared, plus 2 times 5, plus 1, which I believe is going to be, just excuse me for a minute. You can feel free to plug this into your calculator if you have a TI-84. This will likely be a calculator active problem. If not, then you can just do the math. This will be 586. Since f of 1, since the specific value, since 0 does not fall between f of 1 and f of 5. This is me justifying the answer. Since 0 does not fall between, usually it'll ask you to justify your answer if it's proven, like if so, just like can you find is there a value n? If yes, justify your answer. Usually it'll say if yes, but like for this intensive purpose, there is no if yes, so we'll just justify why it's not. Since 0 does not fall between f of 1 and f of 5, IVT does not apply. All right. And therefore it is not on this interval. Because as we can see, it's an increasing function. All right. We'll do another example. So this time we'll do one with a table. So we'll take f of x. Actually, we'll do g of x this time. G of x. Switch it up. So g of x. And then we'll do a few numbers. We'll do 15, 16, 20, 24, 28. And then we'll do 2, 1, -3, 16, -2. And then it'll ask us how many times on the interval 15 to 28 did g of x equal 0. And this uses the same principles as IVT because, of course, in the first problem, we were directly using IVT to prove whether a function was or was not, excuse me, that's my bad, was or was not a part of the function. But this is another use case for IVT, right? So that means Oh, by the way, for the first one, I'll go back to that at the very end. I'll just explain something at the very end. So g of x is equal to 0. We can use IVT for this one because we can clearly see that this is going -1 and this is going up 4, right? And we know that based on IVT, since this function is going from -1 to 3, and since this is a continuous function, so let's just find that g of x is continuous. Since it is a continuous function, it'll always be, it will always hit 0 at a particular point, meaning that is one time that it is hitting a particular point. And then this is another time because 0 is between three times actually. So it's once when you're going from 1 to -3 because you're going down to 0. And then it's one time when you're going from -3 to 16 because you're going to 0, so you're going up to 0. And then this one time again when you're going back down to 0. So 3 times are guaranteed. Or guaranteed by the graph. So 3 times are guaranteed. Usually it'll ask you how many times are guaranteed by IVT. Or like what is guaranteed by IVT. Just like the first one. What was guaranteed? Like we only checked the endpoints to see if it was guaranteed by IVT. We only checked 1 and 5 because we wanted to check those endpoints to make sure it's guaranteed by IVT. All right. That was pretty much it. I'll give you I'll give you a practice problem today. I guess I'll not give you some homework today, but I'll give you a few practice problems. I'll give you 2 practice problems that I'll do one with you, and then I'll let you do one on your own. So we'll call this m of x, and we'll call this L of x. And m of x is going to be equal to x cubed plus x plus 5. And then L of x will be equal to, how should I change this up? Let's do, let's make this ln of x. New function, the natural log function that you should have learned from pre-calc if you took it. Really, you should have learned it from any course before calculus. I'm assuming you know it going into this, just because it is a traditional precursor. My lord, my apologies. Is there a place on either of these functions? Function on the interval 1 through 5 where a value n between that interval 1 to 5 I'm not wording this correctly, my bad. Is there a place on either function where a value n between 1 and 5, closed interval of course, can exist to where f of n is equal to 0. All right. I'll do the first one with you. So the first one, what we do is we check m of 5 and m of 1. So we know m of 1 is going to be 1 cubed plus 1 plus 5. And that's obviously going to be equal to 7. And then m of 5 is going to be equal to 5 cubed plus 5 plus 5, which is equal to 125 plus 10, 135. And since 0 is not between m of 1 and m of 5, it is not guaranteed. On that interval. All right. L of x. My apologies for twisting the screen there, if you saw that. L of x. I'll let you do that one on your own. And then I'll come back to you in a moment. So I'll give you 5 seconds. 5, 4, 3, 2, 1. I hope you paused your screen. You did the problem. All right. So this function L of x, we obviously need to take L of 1 and then L of 5. L of 1 is ln of 1, which is going to be 0. And then ln of 5 is going to be, well, a number higher than 0. It really doesn't matter what ln of 5 is. We can literally just leave it as ln of 5. This is, like, perfectly fine as is. We don't need to change this at all. Because we know that ln of 5 is greater than 0. Because this is what the natural log function looks like. If this is 1, 0... My apologies, that looks a little wonky. If this is 1, 0, then obviously there will be, it'll be an increase from that. And so there is a place between, there is a value n. So there is a value n due to IVT. But you can't just write due to IVT. You have to write due to IVT since it is continuous and L of 1 is greater than or equal to 0, which is greater than or equal to L of 5. My apologies. Therefore, IVT is confirmed. All right. Thank you, everybody. Again, sorry for a few mishaps during that lecture. I'll go over a few of the things that I forgot to go over this lecture, next lecture. But overall, you've hit the end of Unit 1. So this is the end of Unit 1 pretty much. I might go over some things in a last episode just to see if I missed anything. But overall, yeah, that's it. That's Unit 1, everybody. That is the easiest unit of calculus done. But it is the first unit of calc. And it might seem tough, but you'll get used to it. Yeah, but you got to get used to it from here on out because it only gets really tougher from here. All right. Thank you, everybody. Have a good day.